As we continue to develop the work kinetic energy theorem, one thing that we'll start to see as we develop the principle of conservation of energy is that a lot of times we'll want to say, well, we want when we talked about the natural money of energy, we said that you had however much energy at the beginning of a process as you did at the end. It turns out that not all forms of energy, though, are easy to compute. And so, although energy is always conserved, it's always conserved at the microscopic scale. And the macroscopic scale may be a different story. For instance, let's consider the case of a golf ball, which I'm not going to try to draw the dimples. But let's say a golf ball is getting hit by a driver here. Like so. Boom. Now what will happen is for the golf ball to fly off, it's actually going to get, as the driver moves through the position where the golf ball is, the golf ball actually gets squished up really good. Oops. Let's try to draw it like that. It tends to get flattened up and pancaked out quite a bit. And as the golf ball goes flying, what will happen is the golf ball will be returned back to its original shape, but it doesn't do so totally immediately. At some point it'll look more spherical, and then it'll kind of pancake that way, and more spherical and pancake and so forth as it's going along. But with time this will dissipate out, and it'll eventually end up just looking like a sphere again. So when we talk about the macroscopic motion, that's just talking about the golf ball itself. But microscopically, we have to worry about all of the atoms in the golf ball. And we can see that the atoms in the golf ball, let's pick a couple of these right here, they're getting moved around. See, they're farther apart here than they were here. And then over here, they're closer together than they were. So we have, in addition to the kinetic energy that we associate with the bulk motion of what we call the macroscopic motion, macroscopic, so the bulk behavior. We also have a microscopic motion that's going on as well. In this case, each of the individual molecules that are making up the golf ball are moving back and forth as well. So this is the molecule by molecule part of it. Now, to properly, if we were to calculate how much work the driver did on the golf ball, what we would find if we just calculate the kinetic energy, which would be associated with the macroscopic motion, we would find that this wouldn't equal the work being done by the driver. Instead, what we would have to say is, oh wait, the driver, because it squished the golf ball, and then the golf ball winds up oscillating back and forth, and then even after the golf ball itself dampens down, the atoms inside the golf ball are still oscillating back and forth around their equilibrium positions more violently than they were before. And in fact, this will actually show up as the temperature of the golf ball having gone up a little bit, but that's for later treatment. So we have to somehow take this into account. And the way we're going to go ahead and take that into account is to say that there was a change in the thermal energy. So we'll read this as change in thermal energy. And what we will mean by thermal energy here is that this will be the the kinetic energy associated with the microscopic motions, along with the potential energy, which we haven't rigorously defined yet, but it's the energy associated with the bonds holding the molecule together in this case. Microscopic, oops, I can spell micro, S-C-O-P-I-C, C-R-O-S-C-O-P-I-C. So what we're going to say is when the driver did work on it, there was both a change in the kinetic energy plus the thermal energy. So to be more careful in our work kinetic energy theorem, if we need to worry about this kind of behavior, we're going to have to rewrite it to say that the work done, the net work done, is equal to the change in kinetic energy plus the change in the thermal energy. So this is the part that we can easily measure. Usually what's going to happen here is we're going to go through and do all the accounting and figure out if the books didn't balance. We're going to blame that on a change in thermal energy. However, when we get to doing thermodynamics, we'll see that this will show up as a change in the temperature of the object. Okay, so I started there because this is just one of two kind of short topics there. The other thing that I wanted to spend just a moment on is power. This is a term that is not where, unfortunately, the way the word gets used in common language does not necessarily always match the how a physicist would define it. So what we will say is that the power, we will define that as the time rate of change of the energy of a system. So typical units for this are the watt. The symbol is a capital W. 1 watt is 1 joule per second. You can show that the rate at which energy gets delivered, or the power, by a force will be equal to the force dotted with the velocity of the object it's pushing. This is a useful result here, but we won't mess with that particularly here. Now, the important thing here to remember is that this is a rate at which energy is changing. So I'll just go ahead and put this out to you. If you look at your typical electric bill, you'll see that your electric bill will quote that you've used so many kilowatt hours of electricity. So I want you to just pause and ponder for just a second here. What does a kilowatt hour measure? Does it measure energy? Does it measure power? Does it measure something else? I don't know. Go ahead, pause it, and get back with me. Okay, it actually turns out it measures energy. And the way we can get this is to say that a kilowatt, the kilo prefix just means 1,000. So this is 1,000 watts times an hour. A watt is 1 joule per second, and an hour is 3,600 seconds. Cancel, cancel. A kilowatt hour is a convenient way to write 3.6 million joules. And at least in the United States, this is how electricity is usually billed. Other countries do actually bill it as joules, which might be might be more useful, but mostly for historic reasons having to do with how electric meters got constructed. the kilowatt hour was a very convenient unit to use for billing based around how the meters themselves were built. So a kilowatt hour is a unit of energy. It is not a unit of power. Alrighty then. So this was a building up a lot of machinery here with the work kinetic energy theorem. As we go on here, we will finally be able to develop the idea of potential energy and total mechanical energy. And then we'll get to the more general version of the work energy theorem. And then we'll find that with all of this machinery that we've developed, that things will be that this will make certain classes of problems an awful lot easier to solve. So we'll catch you over in those videos.